Hello, everyone. So today we're going to take an informal look at GLOST, job arrays, and just touch on GNU Parallel. So our goal is to find ways that make it easy to deal with submitting a lot of jobs to the queue in a manner that we can conduct parameter searches by sweeping variables. So really what we're talking about is dealing with ranges of numbers such that we can run our program through the range of numbers and generate output into files on the system using the queuing system without writing a lot of scripts, trying to minimize that work. And I think that would be the first instinct if you're going to, if you had a job in your research where you had to conduct a lot of different cases to calculate, you would probably immediately start trying to write scripts and envision how you're going to get each one of those jobs submitted to the queuing system and then manage them individually. Other people have thought of this problem already and implemented these tools, which once you acquire a bit of experience with them, mainly being aware that they're available to you to use and where to find the documentation to use them, are probably the biggest steps to implementing them in your own work. So that's why I've narrowed it down to 3 anyways. Not going to say these are the only 3, but they're definitely the big 3 that are supported on the Compute Canada systems and fairly well documented as well. So we'll probably be going through most detail with GLOST, and so we'll just go to the first. All right, so with GLOST, we want a tool that we can run sequential jobs of short duration. And why do we use this? We're using it to bundle the jobs into a single MPI job. And this in turn handles distributing the jobs over many cores and nodes. So this is important because it's underneath GLOST, it's using MPI to handle an otherwise sequential sort of task list that you need to process. So you don't have to get involved with the inner workings of how the MPI is working in order to use the tool. So you can think of it sort of a high level strategy to handle the problem. And it's going to greatly simplify it because others have already put in the coding effort to deal with the situation that you might be involved with. So it boils down to that you'll set up one input file and submit one job. So that sounds pretty easy if you can then process all your many short jobs. And as well, the scheduler only needs to deal with one job. So GLOST is open source, publicly available, and well documented and available to everyone. So you can use it. You can use it on Compute Canada, but you can also build it and use it elsewhere just as easily. So it's portable. So that's, if you're going to invest your time in doing something, it's good to know that it's readily available to use with other systems. So with GLOST, you're going to create something called a task file. And then GLOST will take care of running the tasks in parallel using, as I mentioned, MPI. All of these tasks are independent such that they're processed, they begin in the end independent of the other tasks. So that's a constraint that's on the work here, the type of problems that you're solving. So when GLOST starts, it reads this task file and it sets up a master process which essentially controls all the other commands that are going to be executed in the task file. Those are the slaves per se, and the lines that you write in the file, and we'll try to take a look at these files. Once each line is complete in the task file, it moves on to the next line in the task file. So basically it has to work its way through the whole task file, which you could consider as an input file. So yeah, I guess I mentioned that. They're on all the, GLOST is on all the Compute Canada systems, as will be the other tools that are covered. And it's covered in the Compute Canada wiki. And it has a module in the system which you load. And to compute the jobs, essentially you're taking the time for each job to run and then dividing it by the number of cores that you might use simultaneously to solve all these tasks. So many tasks are being done at once, and the more you're doing simultaneously, the less time it takes. So within your SLURM, you'll be constructing a SLURM script to submit the GLOST job. So you probably dealt with SLURM scripts by now. And basically the script is there to execute this command, which is shown srun GLOST launch list GLOST tasks.txt. It's this list that contains the commands which are executed sequentially as groups on the system on one or more nodes. So you have to, your job is really to prepare the task file and enter these lines such that it will compute the work that needs to be done. So just for example purposes and following the wiki page of GLOST on Compute Canada, I'm using these examples so it's consistent with the wiki page. And as shown here, each line, these are the lines at the bottom of this slide that are in the task file. And it starts off by setting an argument value to a number in the line. And then if you look at the first line, so narg is 20, this is a command that gets executed by GLOST. So each line is actually a command that gets executed by GLOST. And there can be as many lines in this task, in this list, as you can create. And it could be as complex, but this is just an example purpose. So it sets a variable equal to, say, 20, and then it'll run a command where it's just for demo purposes, it's going to sleep. And then once that's done, it's going to echo the name of the argument and the host name that the task is run on into a file and output that file. So this can be, this is similar to running a program that might output some file, and the program might take an argument. So this is just an example, one step away from a real-world task that you would put in there. All right. And so each line has a different argument number. So you can tell that through your task list, you're now sweeping through an argument. And narg is just generic. It could be a coordinate, could be well, anything that you can imagine the number can be, and it will be processed. All right, so with all that in mind, we can take a look at some examples. You know, I just might just take a second and go to the Compute Canada wiki page to show you that. So I think what I just gave you is a bit of a introductory summary to what's on the wiki page here. So let's take a look at that. So everything you need is going to be found here. It'll give you an introduction. And again, it's talking about the purpose. It's going to bundle your serial jobs into a single job, which you're submitting to the cluster. So your interaction with the queue is very easy because you're just dealing with this single job. All the other tasks are handled within that job. So there is the module. Let's take a look through here. If there's anything new. Yeah, so the example which they've got, here's your SLURM script. Essentially, I've highlighted in green. So it's called run-gloss-test.sh. In my demo, that's translated to script.sh, but it's the same thing. So it contains the commands in a normal SLURM script to load the module and then run the command, which is the GLOST launch is the launcher provided by the GLOST software, and it's going to process the list of commands that you were just introduced to. So arg20, arg21, whatever it needs to do with that argument, what program it runs, whatever, it's everything that you customize in that list file. All right, so let's go to the demo. So here is a sample. What I'm going to do is clear it. So those are just, I just deleted the old data so you can see the starting point. So what we've got in this directory is the script, the SLURM script that you're submitting to the queue. I've got a script called submit. So this contains the sbatch command, which you submit the script to the queue with as per usual. Now the file which is of interest, which I've already set up here, is the list of tasks to process. Now we've seen this already in the slide. So now it's time to run all these jobs by submitting one job. So I've got, so if you cat it with -n, you can count off the lines, number of lines you have in the file. So there's 12 tasks to be run in there, all independent of each other. And to do that, I will again run this submit script, which will sbatch the SLURM script to the queue. And that's it. So it's going to start to process these. so I can check the status of the job. There's an alias called SQ, which is provided by Compute Canada, and it gives you a snapshot of the queue without needing to specify that it's your username. So that's kind of nice because you don't suddenly, the basic SQ command will send all users queued jobs across the screen, which could be thousands of them, so you don't want that. All right, so the job is running. That's a bit unfortunate. So, all right, it is. So the question is where are these jobs running? And it's running on Gray 701. So I can check to see, all right, it's done now. So let's see what it output. It's created all these log files, which if you look above, the objective was to echo one of the arguments and the host name into the log file. So if I cat the contents of these log files, you can see that log 20 contains indeed the argument 20, and it was run on the host name 701. And all the other files correspondingly were done the same way. So it does work. So what's kind of more interesting here? Let's run this thing again. So it's cleaned everything away. So we're running on Gray 768. And now I'm going to run top on Gray 768. That's what I'm doing right now. So what's happening here is you can see that there's two sleep commands running right now, right there. And if you look just above this, these are the processes that are running on the nodes. It's running 26 and 27 already. So it's out there, it goes to 28 and 29. It's processing those. You don't have to do anything. It can't get any easier than this. It's up to 30, 31. And I think that's going to be about it. Right, that's it. So let's take a closer look at the SLURM script to see why was there only 2 sleep jobs running? Because, you know, we had 12 tasks to run. Why didn't they just all take off and start running? Well, that was specified in the SLURM script. So you can see here that it was told to run on one node and run 3 tasks at once. And then the script would load the module and run that. Oh, so then you're thinking, well, wait, there's only 2 sleep commands running on that node. It only crunched through this list. You saw 26, 27, by the time I got it started, got top running, it was already up to 26, 27, 28, 29, 30, 31. So it did them in pairs. So why did it do that? It does that because GLOST, if you think back a little bit, GLOST has this master process that runs on the node, and it's spinning, and it's considered a process by the queue. So really there's only space for 2 others to run because you only specified 3 and the one is taken up by the master. So that's just sort of a minor detail, but so if you want to figure out, well, how long would all my jobs take? That's going to be important because you want to run everything and then know it's going to be done in, you know, a couple days or week or a pretty close estimate. Now, if you're running many jobs and one task not running, one task not counted into the total that are running, it won't make a huge difference, but here it kind of does. So because there's 12 tasks, 2 are running at once, that means there's 6 10-second intervals of tasks of sleeps being run. So it runs for a minute. So let's try to, what was that job name? All right, so it's in the SLURM file. So if I look in my SLURM file, it's got some output there. It came up with, my guess was a minute that it would run. I put the time command out front of the GLOST command, so it's got a minute and 1.4 seconds, so it's pretty close. Now let's check out what the, if I put the job ID under the CEF command, that's another way to get the wall clock time. So it's run for a minute and 2 seconds, so it's bang on accurate with what it did. That's interesting. It's actually used 28% of the memory out of, it's using 256 megabytes per core. If you look at the script, name script, I've even commented that out, right? That's a comment line on the memory, because when you don't put the memory down, that's the default amount that you get. So that's what it said. It's used, it's run 3 processes. Each of them got 256. So it's telling you it got 768 megabytes memory. So that's kind of interesting. So let's go to the next example and see what's different about this one. So clean it up. So it's more or less everything's the same except for this list. And minor detail, well, it's kind of, the idea is that the jobs all have basically the same runtime. So when you get an outlier in runtime, this can be a little dangerous, because when you're submitting the job and you're going to be asking, you're not just going to ask for 3 cores, you could be asked for 200 and who knows, 500 or something like that. And everything takes, I don't know, a period of time until you've got this one job that's going to take 10 times longer. You don't want that, but that's what we've got here. So let's watch how this thing behaves. So what I'm talking about is the first line here. So when you're processing the argument 20, sleeping for 100 seconds versus all the other tasks, which only sleep 10 seconds. So there's still 12. There's still 12 tasks to run here, 12 jobs that we bundled into this one job that we're submitting. But 11 are only at 10 seconds and one of them's at 100. So let's look at this SLURM script again. So we're going to be running again. It's exactly the same as before. 3 tasks. So one's going to be taken up by the master. You've got 2 others. So the one that's 100 seconds, it's going to run. It's because it's the first one. It will start running. Now that leaves the third process out of, like, the second slave, which is the third process. It will be crunching through the other tasks up until the point. Well, it just sort of turns out here that those tasks take a little bit longer than 100 seconds. So it's not quite what I was getting at, where it would create a huge waste of resources if this one task keeps running on forever, because at the end of the day, the tasks finish up at the same time. So that's what this thing is going to show. So when I submit it, let's go like that, and then I can, let's take a look at the run top on the compute node where it is. So it's one of the nodes, and I'm going to look at, let's just take a look without expanding the command. So, all right, we've got the 2 sleepers running, and then let's check out what's going on here. So right there, there's your sleeping for 100 seconds job. And here's the other jobs. We're at 24, so we're holding at 20 there. Now we've got 24 here. And 10 seconds, it'll advance to 25. Here it goes to 25. So GLOST is still getting the job done. So it knows there's an imbalance in the run times, but it doesn't care. It's handling all this stuff for you. Again, pretty powerful. You don't have to deal with that detail. of submitting more jobs and worrying about all the jobs on the system, because there really is only one job. That will just finish. So before it does, use the SQ alias. So, right, only one job ID. And that's, let's see. So it's writing files. We're up to 28. And 29. All right, so it's done. So that, I just want to get the idea, and I'm really going to make the idea permanent now by making you sit through a third example where I make actually the job, that one process that's too long, it actually runs longer than the other ones. So let's see what I mean by that. Now, even after these complete 10, 10, 10, so 110 seconds, this thing is still going to be running on after these ones finish up. So there's not really, it wasn't the other case where they all ended up at the same time anyway. So let's just check the scripts, right? So same thing, it's all the same as before. I'm expecting the runtime to be 200 seconds, right? Because that's going to be governed by the longest job. And I'm going to waste one of the processes. One of the reserved resources is going to be wasted for a while. Unfortunately, because there's an imbalance in GLOST, which we don't want. So let's do what we don't want to do anyways. This is only a demo. All right, so it's submitted. And then I think you know what's going to happen. Actually, there's something else I can show you. No. All right, so we're on Graham 1089. That's where all these are running. And here's, this is a PS command output. Instead of top, it's just snapshot what it was doing when I just ran this command, so it's sort of frozen. So there it's running sleep 200, and then this sleep 10's and NR 23. Yeah, let's do this top commands, pretty informative. All right, so we're on the node again. Got the two sleepers. There's the, I don't know, you want to call this job rogue, something like that. Inappropriate. We're up to 28. It's 29. So we got to go to 31, right? 30. And 31, 10 seconds, countdown. Any guesses what's going to happen when this one finishes up? Yep, well, GLOST knows. It says it needs to finish that first task. So it's only running one sleep command, and one core is now being officially wasted. Now just be lucky this is running for an extra 50 seconds. And it's not, 5 days or something with hundreds of cores. So really important, something to keep in mind when you're using GLOST, because you have a lot of powers in your hands there, so you need to use appropriately. So it's just gonna keep going. So again, it's just echoing the argument 20. It's trying to, once it gets past this sleep 200, it's going to echo the 20.hostname that it's on into that log file, and then it will be done. There it is. So it's done. And if let's sort these output files by date or by time. So I can do a reverse sort. So it's kind of my go-to command for sorts, because it lets me know what was the last file that I was sort of working on. I can find it easily. Well, I can use it in this case here because the last one that was worked on was 20. GLOST did work on this file, and indeed it put it at the bottom. And there it is. Oh, I made my point there. So let's look at what else GLOST can do to get a bit more control on so tab complete and Control R helps you look up your last command that you ran. So what have we got here? We're going to run GLOST on 2 nodes. It's a little bit more advanced because the previous 3 examples are on 1 node. There's our standard SLURM script. Let's batch the script, but let's look at the script first. So here we say we want to use 2 nodes, and we're going to use 2 tasks per node. All right, so there's going to be a master on one of these nodes. So that really means only one, so there's going to be 1 node with a master and a slave, and then the other node's going to have 2 slaves. So two sleeps on 1 node and 1 sleep on the other node. So that's what's going to happen. Let's see if it, or at least that's what should happen. And while it's starting up, so the runtime, if you think about it, it has to be a total of 1 minute and 20 seconds based on, there's, again, it's the same file. Okay, we're sleeping at 20. That's why it's 4 times 20 seconds. So on the 1 node that's running 2 sleepers, each set that it processes takes 20 seconds because they're both done in parallel. So you're running your jobs in parallel here. So let's, can we do that? I don't think that's, yep. All right. So here we got top showing on both nodes. So we got GLOST running on 2 nodes, gray 93 and gray 95. I can just confirm that with the SQ command. Yep, the node lists 93, 95. The master is here on 93, and there's 1 it's spinning, getting CPU. Unfortunately, it uses a CPU, but it's a small price to pay for all the convenience. We've got a sleep running there, and then on the other node, you've got 2 sleeps. And oops. Oh, it finished already. Well, there's not too much exciting there other than seeing that you have control to distribute your task onto multiple nodes. And in fact, I'm actually being a little bit over controlling with this because I'm telling it how many. I could just take that out, how many nodes it needs, and just let the scheduler choose whether it puts it on 1 node or many nodes or whichever nodes come available. So let's see how GLOST handles subdirectories. So let's something different here in the, yeah, so this is out of the Compute Canada wiki. I was scrolling down there and I stopped because it was starting to get a little complicated. So we'll just cover it off here in the demo in some detail. So again, list of tasks to run. There's 12 of them, cat -n. And in this case, you're going to set an argument to the number, make a directory that uses that number. So you can imagine that might be one of your research, whether some sort of number indicating experiment you're working on, processing. And then after it creates the directory, it's going to go into that directory. Now you could theoretically have your program in that directory, you'd run your program in that directory, so your output's going to come into the directory. We're going to sleep instead of running something, and then just echo a file into the directory. So at the end of the day, we're creating a directory with the argument sweeping through some array of numbers we don't know what the numbers are. It could be anything. It's all generic. And then we're outputting a log file into that directory with some contents relevant to what the arguments that submitted to it were. All sounds kind of complicated, but if you can write one line of this, then you've essentially got the whole thing, and then run the sbatch command. Unloading the module, and GLOST just takes care of everything else. So we'll just take a quick, always check the script. All right, so it's back to the beginning again. So we got 3 tasks, really only 2 are going to be running because one's the master. And we're expecting to get directories named run_20, 21, 22 with a log file inside. So they're starting to be created already. So every 10 seconds, 2 get created. So they're coming up in pairs. So 29, 2 more. There, it's done. So it can just, done this before. So that's what it did. So GLOST is giving you the power to create directories, which are somehow correlated with the variable index that you're sweeping through, and you've generated some data into the files that are inside of there containing the information. And I can just run this command. This is the contents of each of those log files. So this example, so before I mentioned that we're using, I wasn't even setting the, I'll do that to you. I had the memory commented out just to get the minimum 256, but if I put it in here, so we're running 3 tasks, now each one is going to get 10 gigs, so this could be a bigger memory problem. So you might need to do that. So I can, and let's take a look at the task it's processing. Same old example, it's back to the beginning again. And so it's running on a node. And the difference here, we're going to see, if you remember earlier, the memory utilization was 29% or something we saw. I think we're going to see a lot less once this finishes up, right? Because the amount we requested was way out of line for what we actually need, which is also not good to do. So run some test jobs before you do anything and check it with the sef command to make sure you're not requesting too much memory. It also, that impacts, really boosts the wait times in the queue. So 29, 2 more. Almost done. Done. And then Ceph this job ID. Ooh, look at the last line. Yeah, I asked for 30 gigs, and I only use 0.7%. Wow, what a waste of resources. But just so you know that you do have the control over the memory in GLOST, and everything else still applies, like choosing appropriately to make sure that you're not you're using it optimally. So the same rules apply, even though you're working within this GLOST framework. All right, so now we've got 15 tasks and a 60 list. So yeah, so there's 60 lines there. I mean, the numbers, this argument's arbitrary, right? I'm starting at 20. It could be any number. You know, it could be a huge number, small number, whatever you're putting in. It's really up to you. At this point, there's only sort of one-dimensional sweep that we're doing. So because there's so many and I didn't want to take too long, we can run 15 tasks at once. So it'll be a little bit more daring. And we're going to try to do that on one node. So it's got a node to do that on, and it's going to go correspond and take the same, well, 15 into 60. So it works out to 8 times 10 seconds. And at 20. Let's take a look on the node. So it's up to 74 already. And it's wrapping things up. All right, good. Not sure if there's anything else we can learn from that one. It sort of breaks us out of using the idea we always have to use 3. No. Okay. All right, so in this example, this one's actually going to run a C program, and it's already been pre-compiled into file a.out, and it computes pi. So each process is going to run the program. Each one is going to calculate pi, and it's not too much accuracy, so it doesn't take very long. It's on the order of other SLEEP 10 we've been looking at. And the list, so here's the file. Now, writing the lists can maybe start to get a bit complicated. So you can't copy paste all those lines. You need some way to approach that. So here, so you might imagine that you need to do something to create your list. So that's what I did. I created a loop and I wrote out each line into the file. So I could blow away the list and just run gen list again to create the list. And once it's ready, then, I mean, because it could be many millions, million lines in there, how many you've got. It could be way more complex. So you can't create each line manually from the wiki page, obviously. So we're going to run it. What does it say? It says the argument again. Let's run this actual program this time. That's great. Let's output the output of the program into the log file. not just the number of the argument and the host name again. Oh, again, we're going to put it in. So I did both. So we're going to get both those things because it's appended, right? So in the first line here, we're going to write the output into the file. And then next time we're going to append some more information, which is the information from before. So let's run it. So what's it doing? It's 2 tasks per node this time. Oh yes, so this is running a multi-threaded example. It's the next step of complication, just to show that it can be done. So it's an OpenMP example of computing pi. And it's going to use 4 cores per task. And it's going to have 2 of them on each node. It's going to be 3 nodes. It's got like 6 going. All that's happening at the end. Expect if you think about it long enough, you'll get 3 times 18. I actually went through this exercise, and this one actually was a little bit off for a particular reason, which I don't want to get into. Well, I did on the login node, which is, there can be differences between login node timings. If you run a time on the login node versus the compute node, better be careful because some of the compute nodes are now kind of getting a bit faster. That can throw everything out of whack. So let's see if it's still running. No, it finished. Oh, that's almost need to run that again. So let's check one of the files just before we do. So the first one, what did it do? So the program computed pi, and then it said the argument's 20. It was on that host. And that'd be similar to the last one. They should actually all, oh, let's add those files. So here's all the log file contents. And they all can, luckily, well, not so luckily, compute the same number. And the only thing that's different is the task number. But you might imagine that the program in a real world example would depend on what this argument is. So I'm not perfect here. It's not because A.out's always doing the same thing. It didn't take the 20 and do something with it. Maybe it should have, the 20, 21, and so forth. Might be just sort of worth running that again and then trying to, I'm not sure what's going to happen if I can snapshot this activity on these nodes. So it's running, and then so we're going to run ps command on each of the nodes and see what it's doing. So we got 2, there's 2, and then 2 on the other node. This is 383. Notice in the left hand, it's telling you which node this PS output is on. So 376, 383. And then the first one is the lowest bound of the node that we got. 3, so that's where we're going to get the master on. And yeah, there it is, burning some CPU. And but at least we're running one process. And here's the thing, that if you look carefully, here's a CPU column, right? Multi-threaded, 4 cores on the multi-threaded. Each one is running 3, oh, this one's not bad, 384%. So using the 4 cores pretty efficiently. It might have been just starting up when I actually did this. So depending where, because the processes are starting and finishing, you know, they take a second or some microseconds to get going. So at some point, all of these would hit 400 during the processing of pi. So more power of GLOST. All right, so now we want to do multi-dimensional parameter sweep, kind of getting in position to do that and start putting all the pieces of the puzzle together. So I'm going to talk 2D, so 2 parameters, but can kind of think of that as 2D. And so let's take, so what are we going to do here? We've got a command that we want to run that takes 2 arguments. So we construct this line, And we set one of the arguments as such. And then I've had to do this, make sure I did this through another example of a do loop to generate this, because it's too many to do by myself. So basically I'm running 1 to 5. X equals 1 to 5, and then y equals 1 to 5. So you've got x is 1, 1, 2, 3, 4, 5, and the y. I guess you can't, no, you can see me hovering with my mouse. It's not 2, 3, 4, 5, and it goes through each one. So every combination is solved, and then it uses that to create a file name to write the arguments and the host name, which could be comparable to your program running, to a log file, log underscore something. So let's, oops, don't want to see that one. So, okay, so we're going to try to run 5 tasks. I didn't put any constraints on the number of nodes this time, so not like it's telling it to use 1 or 5 or anything like that. So it can get as many nodes as it wants. But of course only up to 5, because it's only going to run 5 at a time. So let's submit it. Let's clear up the old data that was there before. And what can we do with this? So they're all running on Gray 126. So we can go see it work. So here we go, we're on the node, and you can see that it's running each task line, writing a file. It just pauses while it sleeps, then it completes. And we're up to 3, 3, 3, 4, 5. So X is at 3. Next thing we're going to be into, X is 4. Yeah, so we're only running 4 processes here, remember? Because the 1 is the master. So I just slow it down a bit. Yeah, just 1 left. X is 5 and Y is 5. So there was an odd number there. So it did the right thing. It created some sort of processed all the combinations and the numbers that we asked it to do. And you can extend that. So, you know, you're sweeping through all these variables, whatever they are, and could be 3 of them. So this one is another similar sort of example. So you need a way to create your list of tasks. So you can do it however you want. But so there they are. This is what you're going to compute in this example. So there's X over in the, let's go to the top. X is 1, Y is 1, Z is 1. Let's take it all the way down to the bottom where they are now 5. All combinations in between. And let's use 25 because there's more, 25 tasks running at once. So it's going to work itself along. So we're up into 2. So we put numbers in here, right? But they could be whatever. Don't have to be numbers. It could be letters, words, things like that, that the program that you're using will depend on the process. so it's done. Check it with SQ. Yep, and everything looks good. Programs would have run according to those almost like coordinates that we've got there. Okay, so I think that goes to the end of the GLOST part. And we can go back to the wiki page, and hopefully now, seeing that in action, you can locate the scripts, lists of tasks that are on the wiki page, and have a feel for what it's doing. There's the one creating a directory. In fact, you can try these examples. And there's a script to do it. You get a lot more examples. Once you load the module, these EB root variables for the package will come available. Fairly often, that will take you someplace deep into the CVMFS tree for that package where related files are located. So it's just saying here, let's copy all the examples into a directory called GLOST examples, and then you could work on those. All right, so it brings us to the job arrays. All right, so again, it's going to let us submit using one script, run many jobs in parallel on the system. And these are, again, independent tasks. And it uses, to make each job different, it uses the environment variable called SLURM array task ID. And that will become a little more obvious when I run a couple of examples, what that is and what this means. Now, you can go through, in GLOST, we generated the list into the file. Here, we're specifying a variable to change using this array argument provided to batch. So instead of having it in a file, it's just put right here. So some ways, simpler, and that's good. And then you have a bit of control over how these numbers will be swept. So here you're processing 0, 1, 2, 3, 4, 5, 6, 7. So each job that's run uses a different value for that, which becomes the SLURM array task. You can make it skip. You can go up in increments. And then you can tell the scheduler to only run 10 jobs at once. So this is how it's done in job arrays. That's different than from GLOST, where we were controlling it in the SLURM script. Let me just go back, because this will help sort of there. Task per node. So it's doing 3. That's not going to work up here. You can put that in, but it won't work in your SLURM script. But this will work. So you could limit yourself to only running 3 jobs simultaneously. Well, why do you want to do that? You just want to get your work done, right? So why should I be limiting myself? Well, I might have a program that's running like a lot of data. And if I try to run all those jobs simultaneously, I might just kill the file system. You might get a phone call. That could be a reason. There could be other reasons. But sometimes you just want to run a certain number at a time to progress through them. That just might be the optimal way to do it without getting into any loading of the file system and everything sort of slowing down and grinding to a halt. Unlikely, but it definitely can happen. If you make a mistake using the file system, you can bring the system down. And when you're dealing with submitting thousands, maybe millions of jobs, you need to control for things like that. So this is the control mechanism for things like that. So they got an example. Now, what's the example here doing? There's a bit of wording, gymnastics down here describing it, but basically here is a line that's going to pipe in the name of a file name based on the SLURM task ID for that. So this could be 1, 2, 3, 4, 5, 6, 7, depending which job it is. The next line is an argument. So program Y takes the SLURM array task ID as an argument. So each job that runs gets either 1 or 2 or 3 or 4 up to 10. So that's what it's talking about here. There's some more details about directories down there. I don't think we're going to focus on this one. So I'm going to run the example for these different situations up there. Job array. All right, so what's inclusive? These. All right, so our starting point is SLURM script, and you don't really need it, but I create them submit script. So I do the same thing every time. That run.out is just some output I got from previous runs. So let's inclusive. So what does inclusive mean? Oh, there's arguments similar to what we did in GLOST, 20 to 31. Those are your 12 tasks that we're going to run. And it's going to actually do the same thing that we did. It's a slight divergence from what's up here, but it connects it with what we did in GLOST. So we're going to sleep, and then we're going to write the argument that the job is running, .hostname, into a log file named according to the argument. And we're going to do that 12 times, and therefore 12 log files. My time estimate, I don't know if you noticed it in all the previous ones, I think it was 5 minutes, so I'm using that notation. That's mentioned first thing on the running jobs page. I'm not sure everybody's level of submitting jobs so far, but knowing the formats, I think it's worthy of a quick second. You're the very first job that they give you in the example of running jobs. Just under that, well, the first thing you're thrown at this time, 0:15:00. What the heck is that? So you can find it under there, thankfully, here. So it's one of the acceptable notations that -- time equals takes. And that one there is going to run for 15 minutes. But I'm using, what I always use is this one, because I don't usually run jobs for seconds, usually in the minutes, maybe the hours. So, all right, back here. Right, 5 minutes should do it, because really actually each one only takes 2 minutes, and there's only 12 of them. But wait a minute, they're all going to run at the same time, so this is going to go really fast. Because, why are they all going to run at the same time, you ask? That's a good question. Because I didn't put this in there. And the default here is to just run it. So I'll try to, it's gonna let's see how many nodes they go on. I increased it to sleeping 120 for this reason, because they're all running simultaneously, it gives me 120 seconds to say stuff about it. So they're all running simultaneously. They've got a, oh no, different job ID attached, which I haven't explained yet because I don't have any slides for this. Yet, for today, I mean, next time. Job ID consists of a couple different components. So we're on 4 different nodes. Oh, we're on multiple nodes here. Let me just wrap it up here and go through this really quick. So that each job, the complicated, I think I'm not going to make it to the GNU Parallel. So let's have that for next one. We can continue, maybe do a bit more with the arrays. Let's make it a 2-parter then. We'll finish the arrays, and because I can definitely do more than the arrays than I have here, but I do have these 4 examples I'd like to get through because this might let you use them. So you're going to be faced with, nice, it's running all the jobs, but not so nice, it's giving you some sort of strange job ID with this underscore, and it's nicely explained up here, and it's also in the Compute Canada wiki. So what I did can make it a little bit easier to ingest. Yes, the SQ command, that alias still works, but it's giving me this ID. So I create another one called SQA that shows you what the actual job ID is. So buried inside these jobs is the array job ID, your standard SLURM job ID, the array job ID, and the task ID. So these are the task IDs here, 20, 21, down through, and here's the array job ID. This 885 thing is kind of constant. And then the original job ID, but that just doesn't show up, that original job ID by default. Because you can reference these things, they want you to re-reference them through the array. So the arrays that are running right now, each entry, task, you might want to call it, can be like canceled independently of all the others. And so you get a little bit more control that way. So that's the breakdown of job ID, and it's here. You can find it by simply going to the Compute Canada wiki page and see job array support for detailed documentation, and right here. It's not very much detail. I might need a bit more in the Compute Canada wiki. So it's done now. Let's see that it, so instead of getting one SLURM output file, we've got many SLURM output files. Each one, I just echoed the command that it ran. And then your log file, you've got the number there. And it ran them it ran what we told it to do. So we did inclusive. So this is going to go really fast. So the listed ones is, let's create a list. Let's use that array in a real script on the real computer and run a real job here, jobs. So let's run 4 of them this time instead of all of them inclusively. So let's submit that. And it's distributed itself on a cluster. So 4 are running. So those are going to take so we're going to get 4 jobs. So I can cancel it by canceling that one job. Oh, yeah, see state, CG, it's in transition. So look at what I did. I just killed them all. Wow, instead of doing them one by one, I just used that SLURM job array ID and killed them all. So that can be really useful. You got a million jobs, or you can pick them out and kill them individually too by referencing that, or the whole thing there, or just that thing there. All right, so we're on a step. We're almost to the end. Oops. All right, so the array, we're going to run 20 to 32. but we're going to take steps of 4. So it's going to do what the previous job did. It's going to run 4 of them, starting at 20, add 4, add 4. That's wrong. That's a typo. There's always 1 in the crowd. And let's I have to do that, but that's our starting point. And just to see that again, it's going to do 4 jobs. All right, great. So let me this time try to cancel it just by, if I do 20. Nope. For some reason I thought that might have got killed. Oh. And the grand finale. Oops, all right, so again. So what do we got here? %4. So we're going to limit 4 to running. So we're doing an inclusive list, all those 20 to 31, but we're going to just limit that to 4 running at a time for some reason, and just to prove that it works. Yes, and notice here, let's see what an SQA is going to tell us. All right, so it's given 4 officially are running, and then it retains that notation for the others. So it hasn't broken them out into separate jobs. So it makes it sort of compact when you view it in the queue. And I think that wraps it up. As I said, we're going to have to do part 2, which will be more on arrays, and then into GNU Parallel, which is, I would say, at least as complicated as dealing with GLOST, but I'm going to say it's probably the most powerful out of all of them. So coming back for more, I'd say is going to be worth the time. Hope this helped. Any questions, you can type them in.